Okay, are we on yet? Dan, are we on yet? Okay, can everybody hear me? Yeah. Okay, good. So you don't have to yell into this. Did you give the lapel mic? What? Does he have a lapel mic? Okay, you're all set. Okay, good. Okay, good. So thank you. Are we on yet for the webcast? Yep. Okay, great. So welcome everybody, both here at Tyson's Corners and everywhere else you are. This is our September meeting for NCOSI, Washington Metro Area chapter, and we'll welcome everyone. I see a lot of familiar faces and some new faces too, so it's very good. Make sure you introduce yourself to everybody wherever you are, and let's move through my little quick presentation so we can get right to the speaker. He's got lots to say. He said he was going to talk for 3 hours. We told him we're going to finish at 8, and so we'll bring him back for a tutorial or something. So next slide, Dan. Oh, I have the clicker. I do. Oh, okay, I have the clicker. It's up front. It's one more thing for me to juggle. And of course, I'll mess it up. Here we go. Okay, so very quickly, I'm going to talk about some chapter news, talk about some volunteer opportunities, some upcoming events, and then get right into Data's presentation. So a little chapter news. Please let's recognize people, chapter leaders, if they could stand up wherever they are. So you make sure you please introduce yourselves to the leaders. I'm standing already, so and Dan's not going to stand, but Dan's our comms chair, so do keep that. Anybody first time at an NCOSI event? Are we have any first timers here? No? Okay. So okay, you don't want to. Okay. Any new NCOSI members? Any new NCOSI members? None here, but hopefully in the other sites. And any recently certified ASEP, CSEP, or ESEPs? Again, none here, but hopefully some of the other sites. So they are coming fast and furious. That program seems to be rolling very well, right, David? Yeah. By the way, we're honored to have David Long here, who's the president of NCOSI. So, David, why don't you stand up, say hi? So. Most of us know David for some time, so he's a good guy. And filling in for a very difficult situation. So that was actually nice of you to take that on. Okay, volunteer opportunities. Sorry. All kinds of things coming up. We do have an election, and since we have Christine Henya here, she wants to say a few words about the election coming up.
Okay, I'm supposed to stand over where you are so that I can see the camera. Hi, we have elections coming up, as he said. Those are the positions available: Vice President, President-elect. You make a commitment for the 3-year term. Spend a year as President-elect, spend a year as President, spend a year as past President. Past President gets to help elect the new people. And there's Treasurer, Programs Chair, Tutorials Chair, Communications Chair, and Director at Large. If you want to know anything about what these positions are doing, feel free to email me. I'm also available at christine.hena@incosi.org. And we're going to try to close nominations at the end of this month and be trying to have elections around October 10th by our bylaws. So get your names in quickly. It's fun. I was membership, and then I've done this, and I expect to continue to be involved because I like doing this. And so I'd like to see more of you involved and meet more people and circulate around to more meetings and have you all be picking up your additional education units and stuff like that for your Sept renewals and things like that, because this is a good way to get them. If anybody has any questions, again, feel free to contact me any way you can. I'm actually the only Christine Hena out there anywhere. I mean, the first 3 pages of Google results, if it's got a K, it's me. So contact me.
Great. Thanks, Christine. Appreciate it. And I have to echo what she said. It is quite an honor to serve the chapter, and it is a little bit of work. We will tell you it is that you do have to take some spare time and free time to do it, but it's well worth it, and you get a lot out of it. So, okay, upcoming events, and I jumped 2 slides. So next month you're stuck with me. I'm sorry, I failed as programs chair to get another speaker, so I'm going to speak. And so what do I know about? Well, DODAF, sorry, the DoD Architecture Framework. So, and in fact, I have a new version of my book coming out this month, and so hopefully I'll be able to highlight some of that for you as well. So November we have a robotics demo, and that's going to be at George Mason University. Oh, by the way, mine's at Nobilis at LaFont Plaza, so that's where I'll be. And we're going to have robotics. Bob, do you want to say anything about that real quick?
The FIRST Robotics program, I think most people know about FIRST Robotics. It's for both high school students and younger kids. There's a partnership between Dean Kamen's FIRST Robotics program and a little-known company called Lego that gets into the middle school and upper areas of the elementary school kids. It's a really, really exciting program. Been around for a few years, 20-some-odd years, and very mature, wonderful organization. And we have the opportunity to get a couple speakers, and I'm trying to get us a couple of robots here so that we can play with those as well. So not that engineers like to play with robots.
Yeah, let's not go there. Okay, December, we are having our annual holiday party. Tentatively right now, I think it's going to be the 7th, and it's going to be at Wildfire. We had actually a really good holiday party, delayed holiday party in June there, and it was quite good. So hopefully this year we will not have the same problem we had last year, which was it got delayed because of snow. Although the Farmer's Almanac is predicting a very cold winter. So just to worry everybody. We'll do our best to make sure you're informed about it. Okay, so let's jump into today's presentations, please. And let me go ahead and get you set up here, but let me get an introduction going at the first time. Dan, are you getting him set up? Okay. Okay, so let me introduce Mr. Matthew Mayer. He's began his civilian acquisition career as an electrical engineer at the Systems Engineering Test Directorate, which is down at Pax River, for anybody who knows the Navy. And he transitioned to the Naval Air Warfare Center Training Systems Division, where he was immediately matrixed to the PEO for simulation training and instrumentation, PEO Strive for the Army. And basically he currently is the director for the Assistant Secretary of the Army for Acquisition, Logistics, and Technology with a Cyber CIO focal. And I don't know what that means, but it must be great. I hope he'll tell us a little bit about that. And Mr. Mayer has a Bachelor of Science degree in electrical engineering from one of our favorite universities, Virginia Tech. Go Hokies. Okay, so and it looks like he's done something with George Mason too, so that'll make those guys happy. Anyway, his bio is is online as well. So without further ado, Mr. Matt Mayer. Oh, okay, you don't need that.
All right, can you guys hear me now? This is still working here. Oh, it fell off. That's what I'm thinking. I got a thing here. All right, how about now? Is that better? Perfect. Okay, great. So thank you, Steve, for the introduction. As he said, I am Matt Meyer. First, I wanted to thank the INCOSE WMA chapter for hosting me today. I think that's great. Yes, I am the director of the Cyber CIO Focal at ASALT. It sounds really impressive. Really, it just means work a lot and get no recognition. But my briefing has absolutely nothing to do with cyber, so I hope that's okay with everyone. A lot of the stuff that I'm briefing today comes from the work of other engineers and scientists and physicists in the nanotechnology field. And I do have a sample of one of the products I'll be citing today. It's a journal peer-reviewed article called A Minimal Tool Set for Positional Diamond Mechanosynthesis. It's about 200 pages. You're welcome to read it. But I read it so you don't have to. I hope that it's not going to be that complicated, though, when I brief. So anyway, so my briefing today is nanotechnology in the age of abundance. And so a lot of people ask me, well, what does that mean? So we'll jump to the next. Oh, I guess I got to click, right? Oop, too much. All right. So thank you, Bob, for the introduction. Lego. In 1932, Ollie Kirk Christensen probably never envisioned that his wooden toy-making firm would evolve into one of the largest, in fact, today, the largest toy-making company in the world. Lego, the Danish word for leg goat or good or play well, basically, he didn't actually start making Legos. He started, he didn't start this until 17 years into the career making plastic toys. And he decided that it would be fun and enjoyable for kids to be able to interlock them in any possible shapes. And today, the company is worth something like $14.6 billion, has a feature film, 6 amusement parks, and worldwide production of about 50 billion Legos per year. So I really enjoyed Legos as a kid, and I think back on that to wonder why so much did I. And Luke, a 9-year-old Lego expert, set me straight. He said, you know, they pay a lot of attention to detail. I never saw a Lego piece that couldn't go together with another one. And he was right. Every single Lego piece ever built fits with every single other piece. And so I think that's pretty interesting. Ooh, I went pressing the button. All right. So Ollie Kirk Christensen probably also never envisioned that Lego would be used for much more than that by engineers and scientists of today. So this is a working life-size car that uses about 500,000 pieces. It runs on 4 engines with 256 pistons each, powered by air. And it will cruise down the highway at a luxurious 20 miles an hour. So this is actually built by 2 guys in Australia. You can see their names here. And actually, you can go to the YouTube and watch the video of the car driving. It's pretty interesting. They probably also never envisioned that large aerospace firms would use it to model a working jet engine. In this case, the Rolls-Royce Trent 1000 jet engine. Again, uses 152,000 bricks, used at the Farnborough International Air Show. Again, working model. So they demonstrate lots of the inner workings of the engine. Another interesting thing that I learned when I was growing up was science fiction. So Star Trek has actually created all the technology we have today. And I'm sure you've heard that before. You can see that there's Captain Kirk in 1967 using the first cell phone, which wasn't actually invented until 6 years later in 1973, and didn't run until the first cell phone network was invented in 1979, 12 years later. Here you can see Captain Jean-Luc Picard with his first iPad, which of course didn't come out until 13 years later. But basically, the sci-fi has envisioned things of the future, and now those are reality today. Another thing that Star Trek envisioned was a food replicator. I know it seems like a mundane item. You put some commands in and it pumps out food, right? Well, I know most of you are aware now that we have replicators. They're called 3D printers, right? 31 years later, in 1983, which was 31 years ago, the first 3D printer was invented. And quite frankly, I didn't know about 3D printers until maybe about 15-ish years ago. It didn't become mainstream until then. And so I have a couple videos related to that. But you'll see today, there's a lot that can be done with them. Let's see if this video will work. We got sound?
A new pair of shoes? Well, don't go to the mall. Print it out yourself at home. We'll show you how. Coming up.
We are in this age right now where you can just get about anything you want right away, right? So what if we said this? What if you bought something online and then you could get it delivered to you in a matter of hours?
That would be a good thing. Well, the technology to instantly print objects in your home is here. KTLA's Doug Melkoff explains how this is done.
If my Star Trek history is correct, humans aren't supposed to see replicators until the 22nd century.
I believe it's a molecular synthesizer of some kind.
You know, replicators, those magic boxes that,
Advanced to water. Cold.
They print out food just like your inkjet prints documents.
One-pan fried catfish.
That's science fiction, right? You can't really print objects.
Smells like the real thing.
How are you? Here in the 21st century,
Better resolution than I thought.
a handful of companies are starting to bring the first generation of replicators into American homes.
That is amazing. And it worked.
Yeah, absolutely. It's a 3D printed glove.
This is the Cube, a personal 3D replicator from 3D Systems.
What's the printing time on something like this?
A couple hours. We actually did that in Washington too.
That arm squirts out a hot, quick-drying plastic and makes whatever you ask it to.
I'm Abe Reichenthal. I'm the CEO of 3D Systems.
Abe's company isn't new.
We're developing a new technology.
It was Wednesday, March 9th, 1983.
That's the night Chuck Hill invented the first working 3D printer. Back then, just printing a Devo hat-type cup was next to impossible. His wife still has that first print.
This is what started the whole industry.
These are going to make your toys in the future.
In the very recent past, these 3D printers were only available to people who had hundreds of thousands of dollars to pay for factory units.
I look at this as the beginning of a personal manufacturing revolution.
Because the Cube
Starts at $12.99. Starts at $12.99. We want to make this easier for everybody.
anyone can design new objects on their laptop and print them out. If you wanted to print something bigger, say a guitar perhaps, you need to design it on your laptop, then upload it to the factory. They'll send you it in the mail. If you're not that artistic, you can actually go online to an iTunes-type store, download an object you want, and print it at home.
This is an interior decor. I think it's a lampshade.
This could be the beginning of a brand new global economy. Right now, they print just plastic and composites. In 100 years or so, maybe we could finally print that fish dinner.
Well, not bad.
And you can print out the shoe instead of having someone slaving away in a factory somewhere.
Or my nano holder. No more sweatshops.
You can also print things that never really existed in the real world before. These are representations of mathematical equations, things in geometry. Now you can hold them in your hands. In Beverly Hills, Dave Melkoff, KTLA 5 News.
Christmas list, okay, Glenn? Just letting you know.
Okay. All right. It is shaping up to be a busy bear season in Lake Tahoe.
So the video is actually a couple years old. I mean, I think most people know about 3D printing, and it's pretty mainstream today. But so where are we really taking it? I'm going to show this video.
It may be the most eye-catching development in printing
since Gutenberg invented the printing press 600 years ago. A machine that can make copies of almost anything, but this time in 3D. It seems like science fiction, but 3D printing is already in use, building hearing aids, jewelry, even parts for NASA. Now the technology is becoming available to anyone, meaning you can turn your garage into a small factory. So what would you build if you could create anything? Have a look. What you are watching is an ear being printed. Layer upon layer, tiny droplets are deposited, building up the structure. So this is someone's ear.
This would be printed to be someone's ear.
Oh my goodness. The project is a type of 3D printing called bioprinting, led by Dr. Anthony Atala at the Wake Forest Institute for Regenerative Medicine in North Carolina.
Same technology you have at your very own home, but instead of printing sheets of paper with ink, you're actually printing tissues with cells.
The premise is simple. Send a scanned image of a body part to the printer, and the machine starts building. Ears, noses, fingers. Dr. Atala's goal is to transplant the parts directly into patients.
So we're actually testing a lot of these structures right now experimentally. The way it works is the cells are able to anchor onto the scaffold. They start making new tissue, and as that starts to happen, this scaffold goes away.
An ear takes between 4 to 6 hours to make, printed with what's called bio-ink, a mixture of biodegradable gel and actual human cells.
One of the big advantages of these technologies is that you are using the patient's own cells. And by doing so, really, you avoid the major problem of rejection.
Dr. Atala has specialized in regenerative medicine since 1990. But it wasn't until this TED Talk 2 years ago that the promise of building body parts caught fire.
90% of the patients on the transplant list are actually waiting for a kidney. You can actually see the printer back here, and that's been printing this kidney structure that you see here. Here it is. You can actually see that kidney as it was printed earlier today.
While implanting kidneys like this is still at least a decade away, it holds the potential to revolutionize organ transplants.
Well, up until just recently, the way that we made these tissues was to actually create them by hand, one by one. When you start thinking about getting these technologies to many patients and creating thousands of these organs at the same time, you need to automate the process, and that's where bioprinting comes in.
Meaning you can make thousands of kidneys.
You could make thousands of organs. You know, you just pick the organ you want to make, then you allow the printer to do them over and over again.
And is this a finger?
This is actually a finger.
Right now, Dr. Atala's bioprinting is in the preclinical phase. Simpler organs will be the first to reach patients, starting with skin.
If this were in fact a wound, it would be dropping real skin cells over the wounded area.
The skin printing project is being funded by the U.S. military with the hope of treating injured soldiers in as little as 5 years. But while Dr. Atala's work is cutting edge.
All right, I'm going to just stop the video there because it goes on and talks about other things that are going on today. But I think it's very interesting to note that in addition to things like food, you could also print any number of other things. Now, I know many of you are interested in nanotechnology, which is why you came here today. I just wanted to highlight, though, that printers typically print 100 micrometer thickness, which is about 16,000 nanometers thick. So that's, quite frankly, very large compared to the nanoscale, and I'll get into that. Oh, hit the next slide. What happens when it doesn't go to the next slide? All right, so you don't actually have to wait until the 24th century to get food. They're printing food already. These were made at Cornell. You can see they have a 3D printed cookie and a printed raw turkey cube with an intercellary cube. Not very exciting or tasty looking, but certainly ability to print food is already here. So here's where it all started. I know many of you know about the physicist Richard Feynman, who won the Nobel Prize in 1965 for quantum electrodynamics. In 1959, he gave this speech. There's not just room at the bottom, but plenty of room at the bottom. I think most people who heard that speech, I think I wasn't around at the time, unfortunately. He did give the speech again, though, in 1984, which I thought was pretty interesting, and talked about updates of the technology. But the premise for his speech was basically this. People for ages have wondered how would you print, say, something large like the Encyclopedia Britannica or the Bible on the head of a pin, right? And so he did a little bit of analysis and said, well, at 1/20,000th scale, you could easily print all of the Encyclopedia Britannica on the head of a pin. And by the way, not all that small. If you take that a little step further, you can, in fact, think about all the books in all the libraries in the world. Roughly 24 million volumes, and how much, if you wanted to reduce that to 1/20,000th scale, the exact same scale, you could in fact fit all of those books on one library card, and you could carry it around with you. So have the entire printed knowledge of the Earth carried around with you. But he said, you know, even that is not really that small. If you go down to the molecular level and you were able to represent characters in the book as, say, atoms, maybe a string of 5 atoms long, and you put it into a 5 by 5 by 5 atom cube, then you could in fact, whoops, went too far. Then you can in fact reduce all of the books in the world to a cube only 1/200th of an inch wide, which on this piece of paper would look smaller than a period, smaller than the barest speck of dust, and it could be floating in this room and we wouldn't even know that all the world's knowledge was printed. And I thought that was a very interesting article. I encourage you to go see the YouTube video. It's about an hour and a half long, but it's very interesting, his speech. So, what is nanotechnology? So I'm sure I don't have to tell you guys, you're all engineers, you know the scales. 1/1000th of a meter is a nanometer, right? We're talking at that level, sort of at the atomic level. This is the Bohr model of the atom, introduced in 1913. Many of you know this has sort of been replaced by the quantum mechanical model of the atom, whereby electrons orbit in kind of a density cloud around the nucleus. But in any event, an atom is typically in the scale of 0.6 to 6 angstroms wide in diameter. So even that, a single atom is smaller than a nanometer. In fact, you could probably fit anywhere between 8 and 10 atoms in a 1 nanometer length. So if you wanted to say, okay, what is the definition for nanotechnology? This comes from the National Nanotechnology Initiative, which was established by the US government under George Bush. They say anything which is about 100 nanometers. So now I guess I question the audience. Is that a good definition? Do you guys think so? I don't know, maybe. So here's the question that I pose. You know, if you think about, okay, let's talk about red blood cells, things that medical students are probably interested in, making robots that help cure cancer, for example. Those are 6,000 to 8,000 nanometers wide, or 200 trillion atoms. Plenty of things in a red blood cell. Bacteria, a little bit smaller, about 250 billion atoms. Viruses, smaller still. Maybe that's why we all get colds all the time. It's because bacteria and viruses are small. Again, about 600 million atoms. Today, the smallest transistors we can print are about 14 nanometers wide. And we're approaching actually the physical limit of being able to print via photolithography on substrates to print chips. And those are even still about 1.4 million atoms. So again, we're talking even in a 1 nanometer cube, you could fit anywhere between 200 and 500 atoms, depending on the element that you use. All right, so what do things look like at the atomic scale? I'm pretty sure I don't have to tell anyone this. Everything is a solid, basically, at that scale. You're seeing molecules and chains of molecules coupled together. This is a carbon sheet we're seeing that goes off into the distance. But at 10 million times magnification, individual atoms are about the size of a BB, from a BB gun. And they would all be packed tightly together, and there's no longer smooth surfaces. Even the tablecloth, very bumpy like this at the atomic level. And also at that level, you can see that those 14 nanometer transistors that we're building today, the smallest ones we can make, would be roughly the size of a laptop, probably like that one, and a whole chip would span out to the size of Belgium. It's very interesting to note, though, that physical properties at that level are much different, but good news is some physics things still apply, so time scales equally for mass, force, and velocity. For example, 1 nanometer per nanosecond is the same as 1 meter per second. And same thing for force and velocity. There is a thing called thermal motion at that level. Basically, all atoms tend to vibrate in place. And in fact, if you were to see atoms that are typically vibrating, like water, for example, they would almost seem like a blur. And I have an example of that. This is actually slowed down many times, but you can see that's kind of what water would look like with some water atoms escaping into the atmosphere as water vapor. I'm going to go to the next slide. Okay, so really what I'm talking about is not just nanotechnology, but I'm talking about atomically precise manufacturing. It's a terminology that's been around for probably about 3 or 4 years now, I think. But basically, they're talking about designing nano machines at the molecular scale. And so you can see, even in 1986, they were able to spell out the words IBM with just a number of xenon atoms. So on a nickel surface, you can see here in the middle is a Nanorex parallel shift reducing gear. And you can see they envision that you can make that out of, like, say, carbon atoms arranged correctly. Here in 2012, we've actually cracked the code on a 1-atom transistor. So if you actually wanted to build chips at much smaller scale, you can see here's the 1 atom right there in the center. And basically, it's able to do transistor technology. So I urge you to go look up some of the references on that. There are some other manufacturing methods out there that I think most people know. For example, chemical vapor deposition is big right now. They're using it to make diamonds. You can make diamonds for as low as $5 to $10 per carat. So don't tell your wife or your girlfriend. But you can, in fact, get very cheap diamonds this way. Large companies like De Beers are not as interested in this technology, obviously, because these diamonds are exactly chemically the same as real diamonds. Yeah, we already talked about some of the other things. The stereophotolithography is what we use for chips, and the sintering and that kind of stuff is what we use in the 3D printing. All right, so I'm going to do some basic chemistry knowledge. I think most of you will get this correct. If I wanted to print a glass of water, what would I need? What elements? Right? Yeah, you would need hydrogen and oxygen. And I heard over here, great, you would also need some silicon dioxide for the glass, right? If you had raw materials, you can see it's mostly oxygen. Oxygen is about 16 times the mass of hydrogen, and it's also more mass than silicon. So conceivably, with very few elements, you could print both this water and glass. All right. Let's do something more fun. You know, obviously, I'm not going to print water my first go around. If I wanted to print a glass of beer, what do I need? Question? Anybody? Water, yes. What else? Yeah, well, the second largest alcohol, right? You would print it straight. You wouldn't print the ingredients. You'd print the beer. I mean, it comes straight with ethanol already, right? And it also includes mostly carbon dioxide, usually about 6 times the size of the glass in carbon dioxide. But the point is those are the main ingredients. Yeah, there is. This is the main ingredients. Yeah, so you're right. The other ones are small percentages. All right. But great. I'm glad that I have a good, smart audience here. Tell me about this one, a potato. If I wanted to print food, what do I need? What is the more water? Exactly. Starch, cellulose, right? I'm sorry, I kind of flipped that too soon. Yes. These are mostly the ingredients. There's about 2% of other things like ash and fat and proteins and stuff like that. But the point is mostly these things. All right. How about if we want to do more like synthetic items, like synthetic rubber? Yeah, well, I'm using polyisoprene, but okay, fair enough, right? It's a hydrocarbon, right? Just like modern fuels today, right? So just hydrogen and carbon. What about plastic? Yes, also hydrocarbons, except for when you want to add some doping like nitrogen, for example, in nylon to make it nice and stretchy, for example. Another interesting thing you can see about this is the chemical structure. You can kind of tell. Like polystyrene is what they use for styrofoam, right? You can see that just based on the leaf-like structure, it easily bonds and holds well, whereas nylon is kind of stretchy. You know, interesting. All right, diamond, I kind of gave this away earlier. Carbon, right? It's a diamond lattice. Not, in fact, the strongest substance known to man anymore, but it does use 4 valence bonds to form into this particular lattice. Now they're working on, obviously, other allotropes of carbon, like graphite and graphene, which I'm sure many of you have heard of. It's a single sheet. It's what you draw with in a pencil, right? You can roll it into a tube and make fullerenes. Of course, they discovered that in 1996. Richard Smalley got the Nobel Prize for that. Oops, a little too far. And you can roll it into a ball, too. This is a C60 buckyball, which I'm sure many of you saw, right? You can use these types of materials to, in fact, dope other elements to make them much stronger. So how many elements did we just show to make all of those things? Who knows? Yeah. 5, right? Great, not that many. Which, by the way, are common materials known to man. I didn't use any special materials like platinum or zirconium or anything like that. I mean, they're found in air, water, hydrocarbons, sand. It's interesting to note that DNA, the basis for all life on Earth, also only 5. So if you were thinking this like Legos, not that many things. All right, so what is this age of abundance that I'm talking about? So most of the information I presented so far came from Dr. Eric Drexler. He's an engineer at MIT. He's currently at Nanorex. He made this book in 2013, I think. Maybe it was 12. But I have read his book. It's very interesting. It talks about how do we move into this new age. If we get to the point where we can, in fact, print things at the atomic level, print maybe being a poor word, if we're actually just manufacturing at that level, you know, we would actually get to this age where we could get anything we want at our fingertips. Dr. Michio Kaku, who many of you know, a theoretical physicist from City College, he also is very interested in this, and he has a whole TED Talk on the age of abundance as well. And so they're very interested in where are we taking this technology and how far can it go. So this video that I'm going to show now was made about 10 years ago, so I apologize for the crudeness, but it talks about what could we do if we really wanted to.
Productive nanosystems, from molecules to super products. Final production made possible by a challenge grant from Mark Sims and Nanorex Incorporated. Future advances in molecular nanotechnology will enable desktop appliances to manufacture products far better than today's best. The cartridges to the left supply simple raw materials to the machinery inside, here shown in schematic form. Products emerge from the top of this box, which holds the heart of the manufacturing system. Each product is built from beneath, layer by layer, by billions of tiny machines, all working together. Near the top surface is the productive machinery itself organized into layers. Machines in the lowest layer process molecules into building blocks, passing them upward to machines that assemble them into larger components, and then to machines that add these components to the product. From a millimeter scale, 1 million nanometers, our view zooms in to the 10 nanometer scale. Each box is 1/10 the size of the one before. Here, at the molecular scale, nanomachines make small building blocks from molecular raw materials. The first machines sort molecules by their size and shape, passing some, rejecting others. Only molecules of the right kind can enter the processing machinery. These molecules contain 4 atoms, 2 of carbon and 2 of hydrogen. The molecules bind to a device that carries them to the next stage. Then, a rotating mechanism swings tool tips into contact with the bound molecules. Each tip presses a molecular tool against a molecule, bonding it firmly. The tools shown here have been analyzed using advanced quantum chemistry techniques. Another tool moves in from the left to remove the hydrogen atoms, leaving a pair of carbon atoms exposed and ready to use. The tools then carry these atoms to their destination, where each pair bonds to a nanoscale building block, making a tiny bit of crystalline carbon, a bit of diamond. Motions happen quickly at this scale. This scene shows motion slowed by a factor of more than 1 million. A conveyor carries the blocks past further machines, which build the blocks step by step to full size. Elsewhere, other specialized machines build blocks of different kinds. A system of conveyor belts and transfer mechanisms carries completed blocks from where they are made to where they are needed. This transfer mechanism moves blocks from one belt to another. The transportation system carries many different kinds of blocks, different shapes, different materials, different functions. It delivers them to the next stage of manufacturing. Here, a programmable machine lifts and places small blocks to make larger blocks. The small blocks bond on contact to form components containing millions of precisely arranged atoms. These can be simple structural bricks or intricate components for mechanical and electronic systems. The completed components are delivered to the final assembly stage, where many machines work together to build the final product. Motions at this larger scale are still quick. This scene shows motion slowed by a factor of 10,000. At the base of each machine, a transfer mechanism grabs components and lifts them from a conveyor. Each is flipped around, then carried up to the underside of the product under construction. Finally, machines lift the components and plug them in place, adding layer after layer to the bottom of the product. When the last layer is finished and construction is complete, the product is ready to be removed and used. The result of this production run is an atomically precise multiprocessor laptop computer with 1 billion times more processing power than today's best. The only waste products are warm air and pure water.
So I should note that, again, this video came out about 10 years ago, and of course a lot of people condemned the authors of this, said it was pure science fiction. Obviously not possible at all. You know, chemistry, in fact, our Nobel Prize winner, the buckyball, Richard Smalley, said chemistry can only be performed in a lab with chemistry. It's not going to, it's the, what did he call it, the dance of a boy and a girl together, and it just takes special things to make them fall in love. You just can't connect them like this. And so he took a lot of criticism and, in fact, fought with Eric Drexler all the way up until the day he died. But the point is, today, actually, people are working on this technology. I don't think for 1 minute that it'll look like that. It'll look like a factory. But I do think that it's possible to put molecular components together, because they're already thinking about what the design might look like. This is a fine motion controller, uses 6 degrees of freedom. Actually, not that many atoms. I don't remember off the top of my head how many it is. But quite frankly, they are already looking at ways to atomically precisely place atoms in one location. You would need some kind of a tool, which has a tool tip on it. You can see this is actually called a carbon dimer. They want to place 2 carbon atoms at a time. And they say that, you know, it has a lot to do with the bond angles, the bond energies, and the bond strengths. So you'd probably need multiple tools. You'd need something to take off the hydrogen atoms. You'd need to have something to put carbon atoms on. You'd need something to place other types of molecules on. So people have already theoretically produced these in simulation. So I put this video together, probably a little bit more, maybe a little bit more realistic based on today's technology. And so I'll talk a little bit about this. So this is a carbon wafer diamondoid lattice, so it's like a diamond surface, only 2 atoms thick. And if you were to use one of these tools to maybe perhaps remove, that's a double carbon bond removing hydrogen atoms. But basically, yeah, in a typical diamond surface, it's covered with hydrogen. It fills up all the unused bonds, right? So you would have to take those off to make something clean to actually build a molecule from. So conceivably, if you can get past the thermal vibration, you can get past the sticky fingers effect, and you can get past a number of other engineering challenges that happen at this scale, you should be able to directly position or directly remove atoms at will. Conceivably, I mean, it sounds feasible. So in this case, you can see you can actually bring the tooltip into contact with the surface. If the bond strength on the tip is weaker than the bond strength of a carbon-carbon bond, of course it'll attach. And that's the whole idea behind it. The great news about manufacturing at this level is you don't actually have to be that precise. You can, in fact, put the carbon on and they will automatically orient themselves to the right bond angles. So as long as you're close, the atoms will touch. So in this case, you can see it's placing carbon. That's I think a nitrogen that it just placed. So again, you can certainly build the chemicals or the components for systems that we need today if you wanted to. Here it's placing some oxygen atoms. So this video goes on for a little bit of time, but this is building probably one of the key molecules that we use in everyday life? Does anybody know what it is? Anybody recognize it yet? Caffeine. Thank you. Very great answer. Good job. See, I knew I had a smart crowd here. Great. All right, I'm going to go ahead. Yes, that's printing some cup of coffee right there. And I'll let that video run out. But okay, so why would we do this? Why bother? You know, obviously, it sounds like a heretic up here. I don't know what the heck I'm talking about. But already today, you can see they're using this technology, not the atomically part, but at least the printing technology to work on a number of problems that we have on Earth, right? Advanced materials and designs, obvious. You know, certainly we could make something a lot cooler than the things we make today if you could print in one or two components. For example, somebody just sent me an article today. They just built the first 3D printed car out of only 49 components, and it only took like 44 hours to print, which is pretty interesting. And you can drive it up to 120 miles an hour. So pretty good. Another problem, obviously, renewable energy. Solar panels today are a big challenge. We're trying to make them at depth, right, so you can see different wavelengths of light and gain energy from each of those wavelengths. Clearly, if you were able to build at the nanoscale level, those could be much more efficient and produce a lot more power output than having the large solar arrays we have today. You can see construction would be reduced almost to the point where we wouldn't need the industrial components anymore. You could print homes right from the ground up. We already saw that they're already working on organ replacement and tissue repair. So a lot of technology there, but really the big thing to me is the environmental factors. You know, today we have such a huge industry impact on our environment, whether it be our air or whatever. Well, you could actually use that as the raw material and draw in the air and pull the carbon out of it and print things out of that. Or you could, I almost propose that guys who owned waste landfills will become like rich in the future because they'll have all the ingredients. You just go to them and get them. All right. So, what does that mean for us, though? I mean, that's a huge impact on our society. Things like shipping, warehouses, stores are not needed anymore. That's a lot of jobs because people could just manufacture the goods right in their home. You could order it online and print it in your house. That also means that data centers become big. The exchange of information a lot more important than the actual product, right? So the intellectual capital becomes the commodity. Production lines that we have today, a thing of the past. We don't even need that. Once it's designed, anyone can have that item. We already talked about the fact that we can make materials with lowered emissions, better, stronger, lighter materials. We talked about energy efficiency. And we can actually do food production if we wanted to, conceivably. I mean, again, it's just a molecular structure. So they're calling this new age where we're able to do these things the age of abundance, meaning a lot of things will change in our society. So here's just a quote. I find that the best advances in science come when there's a crossover between technologies. In this case, we're talking chemistry, physics, engineering, kind of all combined. Engineers often don't think like physicists, and physicists don't often think like chemists. But if we were to think about this problem from all those different perspectives, we certainly could make some headway. So really, that's all I have for today. Lots of additional information, though. A lot of companies working on this. Certainly, I think DARPA has invested a lot in the U.S. government, so clearly there's a lot of stuff. Those are the key players. The briefing that I presented today is from Robert Freitas and Ralph Merkel. So they're actually the ones building the mechanosynthesis diamondoid tools. So I think it's a very interesting topic. So questions?
Why don't we go ahead and start in the room here, and then we'll ask our sites to provide that. Does anybody have a question in the room? I certainly have one. Have you thought about the downside of this? I remember reading a science fiction series by Ben Bova where they talked about nanotechnology a lot, and they had gobblers, which would come, can do nasty things to you and to people. And so have you in your research, have you seen anything?
I can talk to that. So obviously there's the gray goo problem, right? That nanomachines would just continue to replicate until there was no source material left, meaning it would suck up all of us and everything around us and just generate one big pile of gray goo. I think that clearly we could certainly, just like artificial intelligence, put some controls on that and make sure that it doesn't do things like that. Certainly there's a lot of science fiction novels, I'll call them, like Prey, for example, by Michael Crichton, I think one of the last books that he wrote before he died, which talk about nanomachines in swarms that'll come and attack you and kill you in your sleep and stuff like that. But again, with the proper engineering insight into this, I think that people can make those things and, again, apply the same types of logic that we worry about when we think about artificial intelligence and make machines that don't do things like that.
I've got another couple of questions, but I want to make sure we have a chance for other people. Do we have any questions from the field?
Not yet.
Not yet? Okay. Then I'll ask another one. And it's also, I'm sorry I'm meeting negative Nancy here a little bit, but I know I had it for a second ago. Sorry? Oh.
Yeah.
Okay. Just a second. My question again.
Good presentation. Very good, actually. What kind of benefits do you see in terms of energy? How can energy industry can benefit out of nanotechnology?
Well, okay, so I guess I'll answer that in probably two ways. So I think I already talked about the fact that we could maybe produce more energy through more efficient production systems, whether it be hydroelectric power, or air power, solar power, those types of things. Certainly more clean energy. But the second biggest thing is a lot of the new things that we build will be more energy efficient, right? The laptops that we use actually use a lot of power. The projector uses a ton of power. It doesn't have to be like that, quite frankly. If we can get things down to the nanoscale level, again, power scales as well. If you can make a nanoscale transistor, it will use a lot less energy than a 14 micrometer transistor would. And so clearly, a lot of the things that we design could be a lot more efficient in the future, and we could actually save on our power. And the other thing I would say is, there's obviously a lot of interest in fossil fuels, let's say, oil, coal. I know a lot of fights and politics happen as a result of that, right? In the case of nanotechnology and building things atomically precise, most of those elements are no longer needed, right? You can dig up the ingredients in your backyard. You don't have to go to some special place and pull oil out of the ground. I mean, so quite frankly, the raw materials are all around us today. We're just not utilizing them yet.
Anybody else? Anybody else? Just a second.
I'm sorry. You're good.
Am I good?
Yeah.
Sure?
Yeah.
Okay. This is interesting because of the conversation we had earlier today. All of this would effectively, I'll just throw this out, it would destroy the intellectual property world we know today. And I think I just wonder if you would share that position that if anybody can make anything out of anything, therefore knowledge is no longer protected, it's shared by everybody, and intellectual property becomes something of the past. Would you share that thought?
Well, I guess I would say likely it will become a lot like the music industry has, maybe the video industry, right? A lot of things streaming to your home, a lot of things, there'll certainly be piracy. I can't prevent that. But clearly, obviously, human capital, the intellectual property rights of people will become a very interesting topic because, again, you're right, the material good is no longer the important thing, it's the design, right? And excuse me, another interesting fact, though, is today our computers, even all the computers in the world, if you network them all together and use the internet somehow, could not store enough of the molecular structure to be able to build something a normal size, like the human body or a chair or a car or something like that. You'd have to print in pattern matching and things like that. So again, a lot of thought would have to go into the design. And you're right, that clearly would have to be somehow protected. And just like the music industry, probably they would be like a pay-for service for streaming downloads and things like that. But people have to think through those problems because you're right, it would have a serious economic impact.
Yeah, in fact, I did remember my other question, which is the social impact. I mean, this is great for engineers and people who are creative, but we have a lot of people in our society that aren't that creative, and it's going to be one of those issues for them. Now, obviously, with the abundance, food won't be an issue, shelter won't be an issue, power may not be an issue, but then you still have what do they do? and you know, idle hands are the devil's work.
Yes.
It's absolutely true, and it's one of those things that again, I'm curious about your reading. I'm not shooting at you at all.
No, I
But
understand.
did you see anything about that in your reading?
Well, I would say so. The Foresight Institute is very interested in that. Obviously, you know, there's obviously social and economic implications to that, and I think that's why people are afraid of this technology. Unfortunately, I don't think you can stop people from trying to design the technology, but you can certainly try to go about it like smartly. Definitely try to consider those types of concerns. And so I agree. You know, certainly we don't want to get back to Marxism where everybody just has whatever they want, doesn't have to work for a living. That would be a problem. You know, but that means that maybe those people who are store workers today maybe go instead to work in design plants, helping come up with the engineering designs.
Do we have any questions from outside?
Will the slides be posted?
Sure. Well, you have a copy here, so
Yeah.
Be my guest.
That's an easy one.
Yep. Just note that all the work in this again is not my own; it's from other people. I certainly tried to credit them. But you know, to make sure that you post that is their work.
Oh yeah. No, this is great. By the way, I love this kind of research. So, got another question here?
I'm suspecting also from a societal standpoint, similarly to the way there's the current fashion to go organic.
Mm-hmm.
I imagine that there'll be a healthy friction between the desire for the efficiencies of the nanotechnology versus the natural creation for things. You know, people want their naturally created apple that was grown by a tree, as opposed to also the apple in the bin next to it that was nano created.
I agree. And in fact, that's why the technology scares people. I mean, Richard Smalley argued until the day he died that this is not physically possible, and that in fact it all does have to be created naturally somehow. And you know, he has valid points. I mean, he got a Nobel Prize for the buckyball, so he knows a little something about nanotechnology. But you know, that doesn't stop people from trying to create it still.
Let me ask one more question. What prompted you to want to do this research? This is kind of an interesting topic area, and it's a little outside what you historically have done.
Yep. Well, so I guess I've had an interest in nanotechnology for a while because I'm very interested in what comes next. I gave a briefing about 6 months ago now for the War College when I was there, where I talked about how I don't know if the information age is, while it's exciting and important, and I do cyberspace for a living, I don't know that that's going to last forever. I think probably within our lifetimes, many of us, that will shift to some new technology area, whether it be nanotechnology or some biomedicine or new energy sources. But a lot of things will change for us in the future. I mean, I predict by next year, many of us will be wearing the new iPhone watch, for example. Just because it's different, it's new, right? I mean, but the point is that these technologies are coming, and rather than be fearful of them, we should try to embrace them and put the right engineering rigor into them.
Yeah, I was going to say, yeah, Dan already has the other one.
Oh, you already have the other watch?
Yeah.
I have the Pebble. I'm about to go buy the Android one. I'm a nerd.
All right.
So yeah, I think you're right. Particularly the younger folks will pick up some of these technologies quicker than some of us old guys. So any other questions? Any other things?
I'd like to know. I'm a cyber
Just a second, 1 second. Let me, because we have to have everybody else be able to hear you.
So Matt, I'm a cybersecurity guy as well, and cybersecurity is a recognized discipline of systems engineering, and obviously this is a very relevant and interesting topic for systems engineering. So, when are you going to join Incosi?
Oh well.
I'd really like that.
I've been to a number of meetings. I do have friends that are here in Incosi, so I'll have to think about that. The real problem is I don't want to have to get recertified again with the new, what is it? You have multiple certifications.
Oh,
right?
yeah, the CSEPs and stuff like that.
Yeah.
It's okay. Go for the ESEP would be my suggestion. I think you probably have enough years of experience that you can do the 20 years, and probably isn't that hard. So, yeah, it's better you don't have to take the test. So, you just have to be old. Okay. So.
Well, I thank everybody for your time today. I hope this was entertaining. I know it's maybe a little outside the norm. Didn't really talk about engineering all that much. But
I got to tell you, man, I think this was great. And more and more what we need to see as systems engineers, this kind of technology, so we know what's coming. And we're the ones who have to integrate and bring it together. And in fact, if you think about this kind of thing, this is where a systems engineer can really play a major role. So this is terrific. Thank you very much. Appreciate it. And so I guess we're out here. We'll go ahead and see you October 15th. And again, the primary location will be in Nobles, which is near L'Enfant Plaza, downtown DC. So thank you very much. Thank you, Steve.
All right. Thanks, guys.
Well done. Thank you.
Matt, that was nice.
All right. Thanks. I hope I answered your questions.
All
right.
That's always been a very big interest of mine. You read the Benboba books. It's very interesting what they do. They create the diamond spaceships and things like that. It's very cool.
Well, they're actually already doing that today.
Yeah, that's what I mean. Think about
carbon fiber.